everyone, my name is Khaiylah Johnson Bustamante and I will be presenting modeling cloth using finite element analysis. This project was done under the mentorship of Dr. Ruth. Finite element analysis is a method used in simulations and it's used to predict how a material will act under certain circumstances such as temperature fluctuations and material strains. Okay, and here is an example of how finite element analysis works. Basically what you do is you take a material body and you break it up using a system of nodes. The nodes are then connected through line segments, you can think of them as, and it creates a mesh, kind of like a netting in the material, and based on that system of nodes, we get little tiny elements. That's what we're talking about when we say finite element analysis. So here is an example of an element in a three-dimensional problem, an example of one in a two-dimensional problem. Now, right now in this project, we are dealing with structural mechanics. So an important part of structural mechanics is stresses. A normal stress is a stress that is perpendicular to a certain plane. You calculate this by doing the force over the area. And here is an example of a normal stress on a three-dimensional body and a two-dimensional body. Now remember, we're dealing with infinitesimally small elements. So these are tiny things that are part of a larger whole. Shear stresses occur along a plane. They have two indices indicating where they're going on. One index relates to the plane it's occurring on. The other one is the axial direction it is facing. Now, since we are dealing with infinitesimally small elements, our dimensions, delta x, delta y, and delta z, are tending to 0. So we can use rotational equilibrium to see that our shear stresses, as long as they share the same index values, are equivalent to each other. So for example, tau sub xy is equivalent to tau sub yx. So that brings us from 6 shear stress values down to 3. And here is an example to kind of help you see what I mean when I say the shear stresses in comparison to the normal stresses. Now we go to our equilibrium equations, which are based on Newton's second law. We are dealing with a static structural body, so we're only dealing with a free body diagram, which is a summation of all the forces acting on a material equaling to 0. Since we're dealing with a free body diagram, we also have to deal with force balance equations, and in order to make it easier for ourselves, we use a little tool called a Taylor series. And a Taylor series approximation, what you do is you take higher and higher order derivatives of a equation. And since we're dealing again with infinitesimally small elements, we can eliminate the higher order terms in these Taylor series approximations. Due to the elimination of the higher order terms in these Taylor series approximations for the force balance equations, we're left with this. And since we have the area of our two-dimensional element here, we can eliminate it to the other side and we're left with the second equation. And the same thing is done in the third dimension, which leaves us for an equation for the x direction, y direction, and z direction. This is the first set of equations ANSYS, which is the software we are using to compute this, will solve. So thus far we have 3 equations and 6 unknowns in our system. Following that, we go to Hooke's law. In the first dimension, Hooke's law has to do with the change in length over the original length. That is strain. It is the change in length based on stress or pulling. Normal stress in the first dimension is the pulling force over the area of the thing you're working on. And stress can be directly correlated to the strain using Young's modulus. Young's modulus is one of the values we changed in each trial of this experiment. And in the second dimension, it works in the same manner. You just take the change in the value of the certain direction you're looking at over the original value. And the normal strain in the x direction and the y direction can be correlated using Poisson's ratio. And Poisson's ratio is the other value we were changing in each of these trials. We are also assuming the material is isotropic. What that means is if you pull it in one direction, it is going to behave in a certain manner. If you pull it in the other direction, it is going to behave in the same manner. This is an example of skewing, which I will talk about on the other page. Skewing is essentially when you have 2 shear stresses that are perpendicular to each other and they intersect, and then it'll pull in a diagonal direction, causing an angular displacement, as you saw in the previous slide. These angular displacements can be summed to get our engineered shear strain. which is gamma x sub y in this example. Our engineering shear strain can be related to the shear stress using the shear modulus, which is G. The shear modulus can also be related to Young's modulus and Poisson's ratio because the material is isotropic. So in the second dimension, we have our normal strains and our shear strain, which we saw in the previous slides. These are then put in equations that are equating to our normal stresses and our shear stresses. Once we have these three equations, we put it into a 3x3 matrix. The same is done for the three-dimensional example of Hooke's law. We take our shear strains, our normal strains, we take our normal stresses, our shear stresses, and we put them in terms of the strains. Then we put it into a 6x6 matrix. This is the second set of equations used in ANSYS simulation software. Thus far, we have, from our previous set of equations, 9 equations and 12 unknowns. Still not enough to solve our system. And because of that, we use our strain displacement relations. First, we're starting out with the normal strain. The normal strain is the change in length over the original length. And this as well, we take our favorite tool, a Taylor series approximation. And again, because we're dealing with infinitesimally small elements, the dimensions can be taken out in the higher order terms, which leaves us having our normal strain equaling to a gradient of u in terms of x. The same can be said for the normal strain in the y direction and in the x direction. So that's an additional 3 equations to our system. Next, we have our shear strains and the strain displacement relations. So earlier we talked about skewing and our angular displacement. These angular displacements are found to be equal to gradients as well, and when you sum those gradients, you get our shear strain. And the same is true in the x direction and in the z direction. So, based on the last slide and this slide, we have 6 additional equations and 3 unknowns. That leaves us with 15 equations and 15 unknowns, which ANSYS does not take directly. It puts it into a weighted integral form to solve for each singular node or point. All right, so when we did the rounds of experiments, we had certain things that remained constant. For example, in the analysis system, we used a static structural analysis. For our fabric simulation, we made sure it had isotropic elasticity, and we had the values such as the shear modulus. They were based on Young's modulus and Poisson's ratio. For the geometry, we just kept the same dimensions of the fabric. Last but not least, for the model, we consistently used a system-generated mesh, and we had a fixed boundary condition on the positive facing z-axis side. So it was kind of like a side of the fabric was being held, and the other side of the fabric had a force of negative 50 newtons in the y direction. So it was being held on one side, and it moved up and down, okay? All right, and these are the trial variations. Poisson's ratio ranged from 0.3 to 0.1, and Young's modulus ranged from 6 to 8. And ANSYS did all that work. It did the 15 equations in the weighted integral form to get this. All right, and this is trial 1 for the displacement animation. This one had a Poisson's ratio of 0.3 and a Young's modulus, I think, of 6. All right, and this is trial 9. This had a Poisson's ratio of, a Poisson's ratio of 0.1 and a Young's modulus of 8. All right, so ANSYS did all that work for each nodal point. These examples for this piece of fabric had around 1,460, so that's about 1,500. So ANSYS did that systems of equations about 22,500 times, I want to say. Well, it solved 22,500 equations for this body. All right, and plans for project continuation. Next year, what we'd like to do is further refinement in the variations because they were kind of large. It was 1 GPA variation for Young's modulus and 0.1 for Poisson's ratio. And we'd also like to do additional experimentation with mesh refinement for each of the models because that's what's done with industrial techniques to make sure we're as accurate as possible. In addition to that, we'd like to complete the post-processing phase, especially validation. We would like to use numerical analysis, measurements of error to compare it to experimental results in the current body of work surrounding fabric. Last but not least, we'd like to apply the findings to simulate an article of clothing on a body in ANSYS. And that is the ultimate goal of this project, and thank you all for listening.
Hi. Thank you so much. I have a lot of questions, but one in particular. I love these models, and thank you for walking us through the equations. I didn't follow all of them, I want to admit, but I think I get the message. I'm curious because these calculations are assuming that maybe that this is happening in a vacuum, maybe, right? So you will, when you do your follow-up experiments, and like you mentioned with actual clothing on a body, you have to address other forces that might be acting on this material. Is all of that going to be able to be computed based on the formulas that you have, or does it get just infinitely more complex? How would that look?
So when I'm inputting the forces into the software, it kind of breaks it down into the X direction, Y direction, and Z direction, since we're dealing with 3 dimensions. Yeah. We only did a force in the Y direction, -50 newtons. So in order to make it more realistic, we would add it in other directions. Yeah. And there is a current body of work about clothing simulations. However, it's mostly for animation. So we would take some from that body of work and do it more from a mechanical engineering perspective.
Yeah. Awesome. Cool. Thank you.
Yes?
I was just curious because you said a few slides ago that the material is isotropic that you were talking about. Would the equations work if you had a material that was not isotropic and you couldn't stretch it in both ways the same to create these axes in the model?
It's interesting you say that because we know fabric doesn't always stretch the same way in both directions. So thus far, based on it being isotropic, we can only simulate certain types of fabric. So we'd have to do an entirely different model. Like I said, the constant ANSYS inputs were that we were using a static structural model. We'd have to use something else. And we'd also have to use different material properties. So it wouldn't work, yeah. It would be something completely different.
Okay, so I'm way outside my wheelhouse. So how do you define normal versus shear stress? So how do you know the difference?
So the main difference between the two would be orientation and placement. So let me, where is it? I'll go to the slide with the illustration. Okay, here we go. So when it comes to the normal, whenever you hear normal in like a physics or engineering context, it means perpendicular to something. So normal force is a force perpendicular to the thing it's acting on. Same with the normal stress. It is always perpendicular to a plane. So for example, say this is the X plane, you'll never see a normal one going like this or like that. So that's how we know that. When it comes to the shear, it's always working on the plane. So it's kind of like it's friends with the plane, hanging out with it. And this one it's always going in an, axial direction. So in the direction of a certain axis. It's never gonna be on the plane and going diagonal. So they have their certain directions. If it's not going in those directions, they'll have other names, kind of.
Can you just tell us a little bit about like application of your work? Like what do you do now that you've figured all this out? What is the application? I know you're talking about like fabric on a body, but if you break it down for somebody that's way outside of their field, how would you explain this? Yeah.
So right now, the only use of finite element analysis is for animation. That's where my mentor got this project idea because she knew I'm a math person and I like fashion. And so what we want to do is kind of move it to engineering. ANSYS is like the top commercial software for engineering simulations, but it's mostly like screws and steel beams. So what we would like to do is extend the abilities of ANSYS to use it for clothing production, hopefully, and in the future, based on our findings, maybe do some type of partnership with ANSYS where we can either continue this work or they can build upon our work, because we see it. I know one of the sources I used was like for making masks when COVID first started. They used finite element analysis to see what's the best shape of mask to make sure you're not, you know, spreading the disease.